Welcome back, everybody. Hope everyone's doing okay. I have a calendar to share with you. I was looking at the remainder, 5 weeks of class, and given where we're at with respect to chapter, we're doing very well. We are currently, I'm going to start chapter 12 today, but let me share with you the schedule after today. And so what I'm going to do, I'm going to do some changing around a little bit. All right, so today is Thursday, 31st. Okay, so starting next Tuesday on the 5th. And so we got the week of the 5th, the 12th, the 19th, the 26th. Then the week of May 3rd, we have coursework. Okay. Now the final is scheduled for May the 10th. May the 10th, that's a Tuesday. Okay. The final is scheduled for May the 10th. And the 12 right there is highlighted there is the last day to turn in any late assignments. As you know, the assignments, with the exception of the exams, are kept open. Yes, there's a due date, but after that due date, there is a late penalty. So, but you can still finish it. So if you have any missing assignments, some points are better than no points. So you still have the opportunity to take them and finish them up, and then you have a life penalty. Which reminds me, the homework, for example, as you know, there's 2 attempts on the homeworks. If, for example, you only took 1 attempt and you're happy with that, but for some reason you decide, down the road, maybe you did chapter 3, you only did 1 attempt for chapter 3, which was due way back when. And for whatever reason, you want to go back and see if you can improve your grade in that chapter, and that's fine, you can do that. But what happens, Canvas will treat it as being late. So if you do a homework that you turned in at regular time and no late penalty, but you only did 1 attempt and you want to go back and do the second attempt and you get a better grade, let me know and I'll take off the late penalty. Obviously, it's not late because you did it way back when, right? But Canvas thinks it's late, the second attempt. We're trying to get the Canvas people to correct that little feature. So, but if you, like I said, let me repeat, if you've done a homework on time and you only did 1 attempt, and for whatever reason you want to go back and do the second attempt, and maybe you want to up your points a little bit, Canvas would treat the second attempt as being late. But if the points are better than the first attempt, let me know and I would remove the penalty for that. Okay, but only if you did it on time. If you haven't done it on time, then unfortunately, you got the late penalty. Okay, any questions on that part? All right. All right, well, let me, so the final exam is on the 10th. Now, let me go back to April. And so on the 12th, we have exam number 4, which I believe is chapters 10 through 12, okay? Which will be done with that way before the 12th. Then on the 3rd of May, we will have exam number 5, which is the remaining of the chapters, okay? Which 13, 14, and 15. Okay, so what about lecture part? Well, this is what I'm going to be doing. Next Tuesday, I'm going to introduce chapter 12 today, okay? We may finish it, we may not, more likely not. But then on Tuesday, we will continue with chapter 12. And if we do it before the time is up, then the rest of the remaining time is open up to questions that you may have. If not, I mean, I keep it open to 4:15. So if you were done with chapter 12 and you want to go, that's fine, no problem. On that Thursday, that day, I'll be here again, obviously, but I won't lecture on any of the chapters. I will go over the worksheets for the chapter that we just got done. Okay, so we'll go over it and kind of explain the problems for that particular chapter. So basically, that is an opportunity also for any questions you may have. It doesn't have to be for that chapter. You have a question about any other chapter, feel free to bring in the class and we can go over it. Okay. And so that's the game plan for the remaining of the 5 weeks. The 12th, then I'll introduce chapter 13. Okay. If we don't finish it, we'll carry it over to the 19th because we still got plenty of time. But if we do, that works out okay. Also, 12th is an exam day. Yeah, obviously, if you have any questions, I will not go over the chapter. I'll go over any questions you have for exam number 4. Okay, if no questions, then I'll proceed with chapter 13. Then the 14th, then I'll go over the worksheet for that particular chapter. See how that goes. So on Tuesday, I'll do the chapter. On Thursday, I'll go over the worksheet for that particular chapter. And I'll carry it through until the end on the 3rd, which obviously we won't have any chapters to do, but that will be basically a study day. Go over whatever questions you have. I will be here the whole time. If you don't have any questions, that's fine too. It's strictly voluntary. You're not forced to come required, but that's a good opportunity, both that week of the 3rd and the 5th, to go over any questions you may have. So the 5th is not really a worksheet. Let me correct that. It's more like a review, if you want. Review questions that you may have, something to that effect, okay? There is a file in the final part of the final part in the module for the final, which is a review for the final exam. So that's a good resource for you to start looking at it, and you start looking at what the final may encompass. The final consists of 60 questions, all multiple choice. You're given 2 hours to complete, okay? All multiple choice. And obviously your answers will be shown to you ASAP. The 12th, as I mentioned, that is the last day for you to complete any late assignments that may be there. After that, Canvas shuts it off, and then I gotta go and get the grades done. I should, by the end of the week, that weekend, have the grades all completed and then have them officially submitted that weekend. I would notify you by email when I've checked the grades and all the numbers look okay. It gives you an opportunity. I usually wait a day or so before I do the official submission for you to look at it and see to make sure that your numbers correspond with what I have. And then I will go ahead and send out an email saying, okay, I'm going to officially submit the grades at whatever day. But I do know I got to get them in by Monday, which is the following Monday, the 16th. But I normally get them done before that, and that weekend. Okay. Any questions at this point? So you can see here that there's a lot of opportunity here to ask questions and get help from me directly here. Again, if these times don't work for you, sometimes people don't want to speak up and say anything. We can arrange an alternative time for you. That's not a problem. I want to make sure you get assistance either through me or through tutoring, okay? And we're here, 5 weeks down the road, so kind of get you ready for the final exam. Make sure you guys are all prepared and ready to roll to knock that out, okay? Any questions?
Yeah, I have a quick question. I
Sure.
might have missed it.
Yeah.
So on the days that I see where it says worksheet, we don't have actual class. It's just like you'll be available if we need help.
Yeah, I will come and talk, but what I'll do, I'll pull up the worksheet for that chapter and I'll go over the problems.
Okay. And the other question is the final exam, that's gonna be everything from the beginning or midterm until,
Comprehensive, chapters 1 through 15.
okay,
Okay?
thank you.
And yeah, no problem. And like I said, there is a review there to help you out. We will, I need to get the okay. I don't know what, we're gonna coordinate this with the rest of the 130 classes, but right now the exams, I believe, yeah, obviously they're closed, but you can't see your old questions. So there will be a time that we will open them up. So you can go in there and look at the questions you missed, so you can learn from them. And then they'll obviously close up. So as we get further down, I get more information and I'll let you know. So I might have it open up like on a weekend or something, maybe the Saturday or Sunday.
And will the final exam be timed?
Yes, 2 hours, just like all the other exams. The exams are timed at 75. The final will be a 2 hour, I believe. It's 1 hour, 50 minutes.
And do you know approximately how many questions?
Yes, 60 questions, all multiple choice.
Oh, okay.
Okay.
Okay, thank you.
Yeah, no problem. So ballpark, if you figure 60 questions, we have 15 chapters, roughly what, 3-4 questions maybe per chapter, something to that effect. There are old exams on the course website that, including finals, that you can go in there and download them and use them as review. Some of these old exams, obviously, it was when we had face-to-face, but that doesn't make a difference because we can take those questions and modify them so they are done on the online platform. But the questions will be very similar. Okay, so that gives you some assistance and review, some additional resource to help you review for the final. Okay, now if it happens that you can't take that exam, the final exam on the 10th, I can adjust it for you individually. I need to know to tell me why it needs to be moved, but I can do before. I can do maybe one day, but I can't do more than one day after the 10th, like the 11th. I know there's work schedules, a lot of you are working, and a lot of variables in your life, and sometimes things don't work out for you time-wise. We do have some flexibility, but we don't have a lot. So keep that in mind when you're looking at your work schedule down the road. If you got to work, do a 12-hour shift on Tuesday, maybe it might be best to maybe do the final on, say, Monday. Okay, something to that effect. All right, but give it some forethought. Please don't email me the day of. Okay, give it some forethought. Okay, fair enough.
Yeah.
All righty. Okay. Any questions, comments, concerns? All right. Well, let me do this. Let me go into my favorite chapter because it deals with mole. So the very first time I read this, remember, I'm Hispanic and I'm bilingual. And so the very first time I ever saw this subject matter when I was taking chemistry back then, I saw this and I'm like, mole, we're going to talk about the mole concept. No, it's the mole, okay? Now this concept, for some reason, it kind of messes with the mind. I don't know why, but it does, okay? And it's probably because we're dealing with a number. More importantly, a humongous number, a big number, okay? And that's all the mole concept is. It is a number, it is a count of something. It could be bananas, oranges, atoms, ions, anything, tamales, whatever. It's simply a count, but it's a big number. Because if I say to you, okay, a dozen, we automatically, no questions asked, know what number we're talking about, right? when you say a dozen, I say 1 dozen, you know that equates to 12. And that could be a dozen, whatever you want to count. Okay? It's 12 of something. And of course, if I say the baker's dozen, that's 13, right? Okay. Well, the mole is no different than the concept of a dozen. It just so happens that it happens to be a number much, much bigger than 12. Going back to scientific notation, remember, you might refresh your memory on that. But the number we are dealing with is 6.02 times 10 to the 23rd units. And I say units because it's a count. It could be anything. It could be bananas, oranges. It could be cars. It could be students. It could be whatever. But that's a big number. Think about that. Take that decimal point and move it over 23 decimal places. That is a humongous number, okay? And it's a very powerful number because we need the mole to be able to go from apples to oranges, so to speak, okay? Now, I've talked about, we've balanced chemical reactions. We talked about that and said we got to learn how to balance it because we're going to do calculations, right? And if I have a general reaction of, say, A plus B gives me C, okay? Now, I may start off with, let's say, 10 grams of A, okay? And I need to calculate how many grams of A I need. Well, from a gram perspective, notice in the lab, the only thing we have to measure as far as mass is weight, grams. And so 10 grams of B, I cannot equate that directly with grams of A, okay? Because that could be quite differently. Just like the concept, let's say I'm going to use a dozen of eggs as a concept, because we know that if I say a dozen small eggs, right? And I say, okay, compare that to the weight of a dozen large eggs. Obviously, the large eggs, even though we both have 12 in both cases, the large eggs are going to weigh more, right? They're bigger. Well, the same thing is happening here with this reaction here, A and B. I can say I need 10 grams of A, but I cannot directly correlate that 10 grams to some weight in G. What I need to do is to convert those 10 grams of A into moles of A, which then, with additional information, which we're going to go over, I can then determine how many grams of A I need, okay? And so for these chemical reactions, when I'm talking about weight of one and over the other, I can't relate the two unless I go through moles. Moles is the concept. It is the unit that I need to get from apples to oranges, okay? All right, so it's quite important, excuse me, quite important concept as far with respect to calculations. All right, so here's a picture of the scientists who developed this concept way back in, I believe, 1800s. Interesting looking fellow here, right? Okay. Avogadro, he is the scientist who developed the concept of a mole, okay? And the symbol for the mole is the capital letter N subscript A. Okay, that's Avogadro's number. And that number, as I wrote here earlier by hand, is 6.02 times 10 to the 23rd, okay? And this mole, that concept of a mole is no different than the concept of a dozen. We have 6.02 times 10 to the 23rd equals 1 mole, okay? Because if I said to you, all right, 2 dozen eggs, well, 2 dozen eggs is 24. If I said 3 dozen eggs, 36, etc. If I said half a dozen, okay, half a dozen eggs, you're talking about 6 eggs, okay? Unfortunately, when we start talking about a number as big as Avogadro, that for some reason that concept of dozen kind of goes away, but it's no different. Okay, so half a mole would be unit-wise, number-wise, would be half of the 6.02 times 10 to the 23rd. Okay. All right, so let's talk a little bit more about the mole here. How big is that mole? Okay, 6.02 times 10 to the 23rd. If you move that decimal point over, you get a number that's 602.6 trillion. That is big. And if I were to count, if you were to count, say, one particle per second, roughly 1, 2, 3, 4, 5, 6, 7, etc., etc., etc. When you get to the end of Avogadro's number, you would be a fossil, because it would take you at that speed, one particle per second, or basically 1 hertz, if you think about it. Okay, 19 quadrillion years. 19 quadrillion years. That's why we need fast computers that can count, do things much quicker. Take a lot shorter time. Here's some units here to help you out to kind of put you in perspective where that Avogadro's number is. We got a billion here up on top with 9 zeros. A trillion has 12 zeros. And then there's all kinds of other units that I really wasn't aware of until I started looking at these way back when. There's a Google, I believe it's pronounced, that is 100 zeros. That's pretty big. And a Googleplex is a Google of zeros, as a bunch. Okay, so that just gives you some perspective as to the immensity of this. And now what's even mind-boggling, I'm gonna show you here in a bit, that if I were to take 1 gram of water, H2O, I take that back. If I were to 18 grams of water, okay, 18 grams of water, guess what? How many molecules of water I have? 602.6 trillion. Okay, that hopefully gives you an idea. 18 grams of water, ballpark 18 cc's of water, 18 millimeters of water. Not a lot. But within that 18 grams of water, there are 6.02 times 10 to the 23rd molecules of water. Hopefully that kind of gives you in perspective how tiny these molecules are. And the magnitude of water molecules in 18 grams. Now think about this for a second to give you another kind of, to me, a mind blower here. Think of all the water in your body, okay? Much more than 18 grams. We're roughly, 70, 80% water, somewhere in there, okay? Some of us are more bloated than others, but like this guy here. But imagine all the water molecules that are in your body. And then look at the planet of the Earth and think about the ocean. And the quantity, volume of water there, the weight of water. And 18 grams had 6.02 times 10 to the 23rd molecules of water. Imagine all the molecules that are out there in the water, in the ocean themselves. Just an astronomical number. Okay, some other aspects. If 1 mole of softballs, if we had 1 mole of softballs, regular softball, you're a little bit bigger than a baseball, all right? We will have enough softballs to be the size of the Earth. That's how big that number is. And it also should give you a perspective as to how tiny these atoms are, okay? Now, we've been using the periodic table quite a bit. I think so, for multiple things, but let me go back and right here. Let's go to the periodic table. Now, in the bottom below the symbol of the periodic table, there is a number, which is the atomic weight, okay? And which is the sum of, if you recall, the sum of all the isotopes, the weight average sum of all the isotopes for that particular element. So carbon has an atomic weight of 12.01. Well, that number has units, okay? That means that carbon has 12.01 grams per 1 mole, okay? 1 mole. Another way of saying is, if I were to weigh out, or measure out 6.02 times 10 to the 23rd carbon atoms, it would weigh 1 mole, okay? Nitrogen, 14.01 grams per mole. Okay, so you go out there and you weigh out 14.01 grams of nitrogen, you have 1 mole of nitrogen atoms. Okay? And you stop to think about it. Okay, equate that back to the large, small, medium eggs. Obviously, if I got a dozen eggs, small eggs, I got 12, just like here. Each one, in both cases, I have 1 mole of each. 6.02 times 10 to the 23rd. But where they differ, because nitrogen has more protons and neutrons, okay, than carbon does, obviously it's going to weigh more, okay? Just like a dozen small eggs are going to weigh less than, let's say, a dozen large eggs, okay, as compared to, say, a dozen ostrich eggs. Obviously, there's more material. In all 3 cases, you have 12. But they weigh differently. And this is true here with the elements too, because we're gonna, each number there is grams per mole. Those are the units for the atomic weights. It's a ratio. Here comes that ratio again, huh? You're like, I thought I got rid of that ratio business. No, it keeps coming back. Let's take a look at carbon. 12.01 grams per 1 mole. Guess what? Being a ratio, I could write it in 2 formats. 1 mole of carbon over 12.01 grams. Just like the conversion factors we did before, okay? Because now I'm going to be using that atomic weight to get me to either moles of carbon or grams of carbon. The other aspect too is the Avogadro's number. That is a ratio too. 6.02 times 10 to the 23rd units, because it's just a number, units per mole. Okay? And so if you look at nitrogen and carbon again, in both cases, 1 mole of carbon, 1 mole of nitrogen has 6.02 times 10 to the 23rd atoms. And they're going to weigh differently. One's going to be 14 grams and one's going to be 12.0 grams. Okay. All right. So the atomic mass of those elements, unit-wise, is grams per mole. And so if you're ever asked the question, how much does 1 mole of carbon weigh? You simply go to the periodic table and you find its atomic weight, which is 12.01. 1 mole of carbon atoms, okay, weighs 12.01 grams, which is equal to 6.02 times 10 to the 23rd atoms. 1 mole of sodium, its atomic weight is 22.99 grams. Okay, so 1 mole of sodium would weigh 22.99 grams. And you would have 6.02 times 10 to the 23rd atoms of sodium, top 1 atoms of carbon. Okay. Right. So, as I mentioned, that 1 mole is simply a number, entities, like I said, like units, whatever you want to call it, okay? 6.02 times 10 to the 23rd. Therefore, they could be atoms, like written here. They could be ions, they could be molecules, or they could be formula units of, the whole unit of sodium chloride or aluminum oxide, calcium bromide, etc. Okay. In fact, when we go back to the balanced chemical equations that we've been working with, we call those, let's just call this A, B, and we got 2 and maybe 3. Remember I said, hey, keep an eye, when you balance it, remember that coefficient gives us a ratio, 1A over 2B. Well, that number there now in front is, you can now say that 1 mole of A requires 2 moles of B. Or you can say 6.02 times 10 to the 23rd units of A require 6.02 times 10 to the 23rd times 2 units of B, which then will give me 6.02 times 10 to the 23rd times 3 units of AB. That coefficient is simply now moles. 1 mole of A gives me, I need 2 moles of B, which then gives me 3 moles of AB, okay? All right. And so, as I mentioned earlier, that the masses, the atomic weights, have the units of grams per mole, okay? And if you're asked, well, how many grams of mole for carbon, you simply just find its atomic mass, its atomic weight. And carbon is 12.01, okay? Gold has atomic weight of 196.97 grams per mole. And sodium, 22.99 grams per mole. Now, what they all have in common is they all have 6.02 times 10 to the 23rd moles. Imagine this for a moment now. If you're in the lab and you're weighing something out, you're weighing some carbon out, and you weigh out exactly 12.01 grams, you have 1 mole of carbon atoms. If you weighed out 196.97 grams of gold, you have 1 mole of gold. And the same is true for 22.99 grams of sodium. You have 1 mole, okay, of each atom, whichever, 1 mole of each or whatever you weigh out, okay? Now, give us some thought. Let's back it up for a second. If I said to you, half a dozen, right, wouldn't you say 6 or think 6, right? So if I were to weigh, 6 grams of carbon, guess what? Wouldn't that be like half a mole? Okay, because I know that 1 mole weighs 12.01. So half of that, roughly 6 grams, will be half a mole. Okay, and if I were to have, say, 4 grams of carbon, wouldn't that be a third of a mole, right? Okay. 12.01 grams would be a third of a mole. If we give you 4 grams, it would be a third of a mole. And that is true for any of its other numbers. Now, obviously, carbon, when we look at carbon and gold, well, gold is a higher atomic weight, more protons, more neutrons. So obviously, it's going to weigh more than carbon. Carbon only has 6 protons and 6 neutrons there, at least for carbon-12, right? So it's not going to weigh as much. And then the electrons, of course, as you recall, that the weight of electrons are negligible. We don't treat them as having any weight at all. Okay, so the bulk of the weight comes from the protons and the neutrons. So, and that is for individual elements. Okay, but recall, we work a lot with formulas and compounds. So we have to learn to calculate what is called the molar mass. And the molar mass is nothing more. See, we know that all the elements have their own atomic weight. And so when we make a compound, okay, we've done this already. We brought them together with the right number ratio of atoms to make sure that, especially specifically the ionic compounds, that we have enough cations to cancel out all the anions. Okay, we went through this exercise, writing the elements in the ionic form first, so we can put them together in the right ratio. Okay. Now what we're going to do is every atom brings an X amount of weight, atomic weight, to the formula. And we just do, we just add it up. Okay, nothing complicated. And when we add up the atomic weights of all the atoms in that formula, we have what is called the molar mass, because it has the units of grams per mole. Okay, and so you calculate the molar mass of, say, barium hydroxide. Well, the first thing we got to do is, in this case, we need to write the formula, right? So we have to decipher what we have written and convert that to ions first, and then put them together in the right ratio so we know the formula. Recall that barium is a Ba is a symbol, and it's a group 2A element. Okay, so when it becomes ionic, it has a +2. The hydroxides are a polyatomic ion. So you go to the polyatomic ion, and remember that's also the base. Okay, Arrhenius base is anything that produces the hydroxide polyatomic ion. So you go back to the polyatomic ion table, get the formula. The formula for hydroxide is OH negative. Okay, and it has an overall negative charge, and so therefore we need 2 hydroxides for every barium ion. So the formula would be BaOH2. Okay, so we got the formula. Now we do a count for barium. The barium, off the top of my head here, has 137.33 grams per mole. Now, where did I get that from? The periodic table. Okay, oxygen. Okay, each one is 16. All right, so we have 16 times 2. We have 32 grams per mole for the oxygens. And then hydrogen brings in 1.01, and there's 2 of them. So it brings up a total of 2.02 grams per mole. Okay, so you see I'm making a little grocery list, if you will, right? I got 1 barium, 2 hydroxides, 2 hydrogens. Tally up the atomic weight that each one brings into the table: 137.33, 32 grams per mole, and 2.02 grams per mole for the hydrogen. Okay, tally that up, and you should end up with we got the formula first, and the atomic molar mass is 171.35 grams per mole. Okay. So what does that tell you? 2 things. We got another ratio. Okay, 171.35 grams per 1 mole of barium hydroxide, that we can write like that, or we can invert it. Okay, because we will use these ratios to calculate either grams or either moles, just like we did the conversion factors. Okay, we had that ratio, and we put the unit that we're looking for on the numerator. And so if we're looking for grams, obviously we're going to be given X moles over here. Moles cancel out to give us the answer. If we're looking for moles, we're going to be given X grams over here. We multiply through because the grams cancel, leaving us with moles. Okay, that's how we set up the problem. And these conversion factors, we start off with grams of barium hydroxide, and then They might be reacting with the base to neutralize it. And so we find that ratio of the acid to work with from the balanced chemical equation. And then that takes us from hydroxide to an acid in moles of acid, from grams of barium hydroxide to moles of barium hydroxide based on the molar mass, to moles of acid based on the balanced chemical equation, to grams of acid. Okay, notice how we did. We have some examples we're going to do, so bear with me for a little bit. I'm trying to bring it all together here. But notice how we went from grams of hydroxide all the way to the other side to grams of acid, some acid. And in order to get from that point A to point B, we needed to go through moles, because the moles is the common factor between the two reactants. Okay, we couldn't go directly from grams to grams. We have to go through the moles. And we do have a flow chart. They're going to put this all together for you so it can, won't look sound as complicated. Now, another aspect about this, if you hope, maybe you noticed here, but the barium brings in 137.33 grams. The total weight is 171, and so if I were to take the 137.33 contribution of barium, and I divide that by the overall molar mass times 100, guess what? I got me a percentage of barium for that barium hydroxide. If I were to take the 2.02 for hydrogen, this is barium, this is hydrogen, divide that by the overall 171.35 times 100, that would equal to the percentage of hydrogen in barium hydroxide. Then the 16 divided by 171.35 times 100, I'll let you do the numbers. That gives me a percentage of oxygen. And you'd be interesting to know that that percentage we just calculated, that you can calculate here, I didn't put the numbers here, but that percentage is true for any molecule of barium hydroxide. Okay. In fact, we use that percentage in my day working with chemical compounds and making them. We will get them, clean them up, calculate what the formula is, determine what the formula is, calculate what the percentage is, what we anticipate it to be, send a sample off for analysis, and when it comes back, if we're correct, then that percentage would be correct based on what the lab results and what we calculate. And that's additional information as to, yeah, we made that compound, based on all the other information, not just the percentage. Anyway, gives you a little heads up on that. All right. So going back to Avogadro's number, as I stated earlier, it's a ratio. Okay, just like the molar mass is a ratio, the atomic weight is a ratio. Atomic weight is a ratio, grams per mole. Molar mass, which is the sum of all the atoms in that compound, is a ratio of grams per mole. Okay, and Avogadro's number also is a ratio of atoms or molecules or whatever per mole, which you can write in one or two ways as written here. And we can use that ratio to do some calculations. For example, you may be asked the question, how many calcium atoms are in 0.25 moles of calcium? Okay, and so we want to know how many atoms of calcium are in roughly a quarter of a mole of calcium. So just like we did the conversion factors of going from English to metric units, same system here, okay? We write down first what we're given. We are given 0.25 moles of calcium, okay? Obviously, we're going to have a conversion factor here because we are looking for, and then we write down what we're looking for, because that's our map to figure out where we got to go, not get lost. We got to figure out how many atoms of calcium. That's where we're going. That's what we're looking for. And so the fact that we start off with moles, I need a conversion factor that will get rid of moles and give me atoms. Okay, so my units would be atoms over moles. Okay, and I have that here because I have Avogadro's number. I got 6.02 times 10 to the 23rd atoms of anything. In this case, it is calcium per 1 mole of calcium. Okay, 1 mole of calcium has 6.02 times 10 to the 23rd atoms. 1 mole of bananas is a lot of bananas, 6.02 times 10 to the 23rd. 1 mole of apples is 6.02 times 10 to the 23rd. Okay, it may sound redundant, and I'm probably going to be redundant here in this chapter, but it's for a reason, okay? So then look at my units. Moles cancel, moles of calcium cancel, leaving me behind units of atoms. So now I got the problem set up properly. This is where you come in now with your calculator to refresh your memory on how to input scientific notation. Remember, you have either the 1 or 3 buttons, the EE button, EXP button, or that button has X 10 to the X power, okay? Plug that in and boom, do the calculation and you have an answer. Let me clear the mess here. And you have the following. So in a quarter of a mole, 0.025 moles of calcium, you have 1.51 times 10 to the 23rd calcium atoms. Okay, so 0.25 moles of calcium. That's, like I said, a quarter, right? 1 mole of calcium weighs 40. So approximately a quarter mole weighs about 10 grams. Right? So in about 10 grams of calcium, I have 1.51 times 10 to the 23rd calcium atoms. Okay. You might ask, well, how do we know I got about 10? Well, I'm glad you asked. Okay, let's figure it out here. 0.25 moles of calcium. And I want to know what does that correspond to with respect to grams of calcium? All right, well, I need a factor here that has moles in the denominator and grams in the numerator. Well, guess what? That is the atomic weight of calcium, which is 40.08 grams in 1 mole of calcium. Moles cancel, and it's roughly about 10 grams. You see how that works? Okay, so roughly 10 grams of calcium, you have 1.51 times 10 to the 23rd atoms. All right, the next one. Similar scenario, we are calculating the moles of 3.75 times 10 to 27 molecules of oxygen gas. Okay, now read the problem carefully. Okay, because they didn't say oxygen atom or just atomic oxygen, they said oxygen gas. Remember, being a gas means this that we're talking about diatomic O2. And its molar mass would be 32 grams per mole, right? Because each atom, each oxygen weighs 16 grams. If we were talking about atomic oxygen, we would use 16 grams. But the problem said oxygen gas, which is diatomic. So we need 2 molecules of oxygen. Okay, and that gives us a molar mass of 32 grams per mole. All right, now let me clear this up. Okay, so 3.75 times 10 to the 27 moles of oxygen, okay, molecules of oxygen. And I introduced the grams, and I'll explain that for a second, why I use diatomic. So we use Avogadro's number, okay, like we did up here. So now it's moles in the numerator because we want molecules to cancel. And that means that we have 6.02, 6,230 moles of oxygen gas. Okay. Now the question is, how many grams does that correspond to? All right, so 6,230 moles of oxygen gas. Okay. We want to know how many grams of oxygen gas that corresponds to. So I need grams in the numerator, moles in the denominator. Okay. Since we are talking about oxygen gas, it's diatomic. So we got 32 grams per 1 mole for oxygen gas. That is the molar mass for oxygen. So take that 6,230, okay, multiply it by 32, and that will give you the actual mass of oxygen. Okay. But the key here, you have to do this calculation to remember they talk about oxygen gas and not molecular, not atomic gas, which would just be 1 oxygen. And that would be true for all the diatomics, okay? So be careful when you read the question. And remember that 9 times out of 10, you're probably talking about the diatomic form. Okay, so right now we've been just dealing with moles to moles, or moles to molecules or units or whatever, you know. We haven't talked about grams. I touched on it, okay? But we're going to, because in the lab, you know, when you go in and measure something in the lab, the balance doesn't say moles, it says grams. And so you weigh things out in grams, right? But you need to do calculations to determine in moles. So you start off with grams, you need to convert that to moles, and then that mole information is used somewhere else for further down the calculation. So molar mass, as I mentioned, has the units of grams per mole. Molar mass is the sum of all the atoms and their respective atomic weights that they brought to the molecule or the compound, okay? And being the units grams per moles, we can write it either as moles per gram or grams per mole. Which one we write depends on the question asked. For example, the previous one we went from molecules of oxygen to moles of oxygen. Then I introduced getting from moles of oxygen to grams of oxygen. And that's what this is doing. It tells you I have 1.667 moles of oxygen gas. How many grams does that consist of? Okay, is the question. And so obviously, again, we're talking about moles of using oxygen gas. So we're talking about the diatomic O2, which means the molar mass is 32 grams per mole. Notice they are set up because we're looking for grams. Grams is going to be in the numerator. Okay, moles cancel out, leaving us with units of grams. Okay, so that means you set that up properly. Now it's up to you to punch in the right number. So it's 32 times 1.667. And that tells you that that weighs 53.34 grams. Okay. Okay, here you have 45 grams of silver. So we're going from grams of material. Here you can think of it in general terms, okay? From grams to moles. Obviously, to do that, I need the atomic weight. And the reason I say atomic weight, because it's just silver, it's the element. When we talk, you might get confused sometimes when I say atomic weight versus molar mass. Remember, atomic weight is simply the atoms themselves, the elements, okay? Molar mass deals with the compound cell. We have more than one element in there. That's the difference, okay? So here, in this scenario, we start off with 45 grams of silver, okay? We go to the atomic weight on the periodic table for silver, and that corresponds to 107.87 grams per mole. But I want to invert it because I want moles in the numerator, because that's what I'm being asked for. And I want grams in the denominator because I want to get rid of grams, leaving me with moles. So if I weigh out 45 grams of silver, it is roughly a little bit shy of half a mole. So 0.42 moles exactly. Okay. Now don't lose track of your sig figs here. Now, one point to remember, when it comes to the molar mass, atomic weights, those are, you don't use those to determine your sig figs. Use your measurements. Remember that the atomic weights come from the weighted average of whole numbers. Remember carbon 13, carbon 11, carbon 12, carbon 13, carbon 14, either a certain percentage in the environment of each isotope. And so we average out 11, 12, 13, and 14, which normally if we would have just averaged those out straightforward, it's what, roughly 12 and a half, right? But it's not, we do the weighted average. So there's more carbon 12 out in nature, like 98%. So it's going to contribute more. So the atomic weight comes out to be, the weighted average is 12.01, okay? Anyway, and so taking the average of whole numbers gives you an infinite number of sig figs, and therefore we don't use the atomic weights to determine the number of sig figs. Okay, 45 grams of silver that corresponds to 0.42 moles of silver. Okay. Here, the question is this. They says, how many grams is a 0.055 moles of water? All right, so we first need to figure out the formula for water, okay? Hopefully we all know that formula for water is H2O, okay? Next, we need the molar mass of water. Well, we have one oxygen, which is 16.0 grams, and we have two hydrogens, each one bringing in 1.02. So we have 2.02 grams per mole for the hydrogens and 16 grams per mole for the oxygen. So we have a molar mass for water as 18.04 grams per mole. Okay. Now, you know, the example I used earlier, I said if I weigh out 18 grams of water, in this case, 18.02 grams of water, I have 1 mole of water molecules, or 6.02 times 10 to the 23rd. Okay, a lot of water molecules. So we need the molar mass here. All right, and we're looking for grams. And we start with moles. So we got 0.0554 moles of water, okay? I need a conversion factor to get me to grams of H2O, right? So I need grams in the numerator, moles in the denominator. So that corresponds to 18.02 for 1 mole of oxygen, 1 mole of water. So 18.02 times 0.554 should give me 0.998 grams of water. Okay. So 0.0554 moles of water corresponds to almost 1 gram of water. Almost 1 gram. Okay. Here, let's break down the question, okay? Break it down steps so we know what we're looking for. And break it down like determine what we know and what we don't know and what we have to help us out to get to what we don't know. All right, so we're looking for grams. So obviously over here, we're going for grams of K, which is potassium. Okay. Well, they're saying here that there are 4.75 times 10 to the 16 atoms of potassium. Okay. Well, we can't go directly from atoms to grams. We can't do that. We don't have any relationship there. So no direct relationship. But we can go first to moles of potassium, right? Remember, that's the common factor. If I get everything to moles, then I can divert to wherever other units I need to go to. So looking for potassium, that means that more than likely I'm going to use its atomic weight, which is 39.10 grams per mole. I find that from the periodic table for potassium. I'm going to need that, okay? And notice that gives me 2 grams via moles. So Avogadro's number I'm going to need 6.02 times 10 to the 23rd units. In this case, units happen to be atoms, okay? But notice here, I can go from units to grams via moles. That's our common value to get from point A to point B, okay? And this, if you recall, this is why you might look at this and say, well, I don't see any connection here. But the whole point of doing that exercise I did way back when, remember I had that conversion factor where I dealt with dental hygiene students and I think how many bananas? Okay, you probably were thinking, you know, oh, it's kind of nuts. Why? It was not. It is nuts. You can go from DH students to bananas if you have conversion factors to get you from point A to point B, and you set them up properly. We're here, okay? And so obviously I need a conversion factor that gets rid of atoms. Right, so that's got to go in the denominator, and it puts me into moles. All right, so this is Avogadro's number, 6.02 times 10 to the 23rd in 1 mole. So 6.02 times 10 to the 23rd atoms per 1 mole, my atoms cancel. Okay, for potassium, I got moles here. Well, next conversion factor would be my atomic weight, molar mass here, atomic weight. And I'm looking for grams, so obviously, I got 39.10 grams of potassium per 1 mole of potassium. Notice my moles cancel, leaving me unit-wise with grams, which is why we emphasize this technique to help you get from point A to point B. This requires 2 conversion factors, but when we really get into the calculations, you're going to find that you're going to need at the minimum at least 3 conversion factors. We'll move over to 1 more conversion factor. Okay, here, let me clear this up. All right, so you notice here's my conversion factors, and my units all cancel out, leaving me with grams of potassium at the end. Okay, so think about this number that one calculated. Okay, I started off with 4.75 times 10 to the 16 atoms. So, you know, take that 4.75 and move that decimal point over 16 positions to the right. That's a humongous number, huh? All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So here's my decimal point. All right. So that's how big that number is. Humongous number. It's how many atoms of potassium they are telling you that you have. Okay. Once you go through the calculation, look how tiny that weight it corresponds to. 3.09 times 10 to the negative grams. We don't have any balances that can weigh that accurate, at least in the standard lab. Our lab, if we were in the lab itself, could weigh to 4 decimal places. This is going to quite a bit. So very, very tiny, tiny, tiny amount, but a humongous number of atoms. So give you some perspective as to how small these atoms are. I was asked the question a long time ago is, have we ever seen an atom? Okay. And my answer is not directly. Okay. We have indirectly, and those are for big ones like some big molecule, big atoms. And the way it was done, there was a piece of equipment that was developed by IBM multiple years ago, which kind of operates like a stylus of a record player. Us old timers, that's how we used to listen to music, with a little stylus, a little needle, vibrated. I know you guys still use it now when you're doing some music, but there's a stylus, a very, very sensitive stylus, and it will pick up on movement, very subtle images and so forth. So the result was that it actually took an image of, say, carbon atoms that were circular in shape. Granted, this is the 80s, the resolution has gotten better, but it's like looking at a planet, a few thousand light years away, and you're getting fairly close in a resolution. You can see some detail, but not very clean. But it's still, you can see the trend where you have the atoms in circular shape. So that, there's also pictures of images of polymers, conducting polymers, and very, very exciting stuff. It's amazing that happened. All right, well, I'll tell you what, let me stop here. I don't want to give you time to digest what we talked about with respect to the mole. We're going to take it one step further here. Okay. All right. So let us stop here.